point, you're pretty familiar with the concept of molar mass. We've been dealing with this for a while. Molar mass is the amount of mass in 1 mole of a substance, and that's different for all different substances. Now today we want to look at something called molar volume, and this only applies to gases, and it's not different for different substances. So the molar volume would be how much space does 1 mole take up. Do you see the analogy? So molar mass is how much mass is in 1 mole, how many grams is in 1 mole. And that will be different depending on the size of the individual atoms, because a mole is always a fixed number of particles. So bigger atoms are going to weigh more, and if you have a mole of them, you will have more mass than smaller atoms which weigh less, and if you have a mole of them, you'll have less mass. And that hopefully makes sense to you. Now with gases, it doesn't matter if the molecules are big or small, because the size of the molecule is so tiny compared to the spaces between them that they ignore each other, and they will spread out apart from each other the same amount, whether it's a big molecule or a small molecule. It totally doesn't matter. So therefore, the molar volume, the amount of space 1 mole occupies, is going to be the same no matter what the substance is. But it can change based on the conditions of the gas. Now, we've already been through a whole unit where we learned about gases, so you know that. You know that if you increase the pressure, you're going to push those particles closer together, and there will be more particles in a smaller space. Whereas if you decrease the pressure or increase the temperature, the particles are going to spread out more. You'll have fewer particles in that space. So those conditions will definitely affect your molar volume. They will affect how much space does 1 mole take up. So at some point along the way, somebody decided that they would define something called standard conditions. So standard temperature was defined as 0 degrees C. And now we know that when we're working with gas laws, we have to use Kelvin. So that is 273 kelvins. Standard pressure was defined as 1 atmosphere of pressure, which is what you would expect them to define it as, because that's typical atmospheric pressure at sea level. So those are our standard conditions. And abbreviated, that's STP equals standard temperature and pressure. So those are our conditions for standard temperature and pressure. Now, hopefully that looks familiar, the ideal gas law. So we can figure out the molar volume of any gas under these conditions of standard temperature and pressure by using that equation. So let's do it. So the pressure we just said would be 1 atmosphere, 1.0000. The volume we'll leave as V because that's what we're trying to find out. How much volume will 1 mole occupy? And we're going to put in 1 mole because that's what we're trying to find out. How much volume does 1 mole occupy? R 0.08206 liter atmosphere mole kelvins. And then temperature is 273. So if I want to divide both sides by 1 atmosphere, that gets me volume all by itself on this side of the equation. And let's try it. 0.08206 times 273 equals 22.4. So that is liters per mole. And that is the molar volume of any gas at standard temperature and pressure. So that's kind of like a magic number. If we know that we are under standard conditions, then we can use this number to figure out how much gas we've got. So let's do a few problems here. Put that number up here so we don't forget it. So that is our molar volume of a gas. So a typical problem might say something like this. If you have 65 liters of gas under conditions of standard temperature and pressure, how many moles of gas are in your container? So 65 liters. How many moles are there? Well, we know that 1 mole occupies 22.4 liters. So what will we do with this? Another way to say that is for every 22.4 liters, we've got 1 mole in there. So what you're going to do is this. You're going to say 22.4 liters per mole. So every 22.4 liters represents 1 mole. So if we divide this number by 22.4, we get the total number of moles. Another way to look at this is just to say that liters and liters will divide out, which leaves us 1 over mole. So the two 1 overs cancel each other out, and that leaves us with moles. Another way to handle this is just to memorize it. All right, 65 over 22.4. Answer is 2.9. So there's problem number 1. Let's do another problem that has the opposite kind of scenario, where instead of being given the volume, we might be given the number of moles. And many times in a problem it will tell you what gas you have, so it's important that you kind of keep in mind that you don't need to know that, so don't worry about it. So let's say that you are going to be given 3.2 moles of argon gas. And we don't care that it's argon gas, because any gas has the same molar volume. We only care that it's at standard temperature and pressure, which we are told that it is. So 3.2 moles, each mole occupies 22.4 liters. So notice that moles are going to cancel out as we do the math here. So 3.2 times 22.4. 71.7, no, two significant figures, 72. And that will be our final answer for that. Now, if we wanted to, we could define some other set of standard conditions. Because maybe we're scientists that work in a particular lab that have to use particular conditions. And so in our lab, those become the standard conditions. So let's just make something up. Don't tell anybody. It's not really standard. Let's say that in our lab, we are always using pressurized gases, and they are pressurized to a pressure of, let's say, 5 atmospheres. And let's say in our lab, we always use gases at regular room temperature, which is not 0 degrees Celsius. And so normal room temperature is defined as 298 Kelvin. I mean, there's lots of different room temperatures, but that just seems to be accepted as a standard. So let's go back to our PV equals nRT and say that, all right, so our pressure in our lab, we are always using 5 atmospheres of pressure. And we want to know what's the molar volume then. And again, we only care about 1 mole for this particular calculation. R doesn't change. And, oops. And our temperature is going to be 298. Because that's room temperature. So we want to be under higher pressure and normal room temperature. So to solve this, we're going to divide both sides by the 5 atmospheres. Get rid of that over here. And so our molar volume, in other words, the volume of 1 mole of gas, becomes something different. 0.08206 times 298, and then divided by 5. We've got, how many significant figures do I want here? Well, if I decide that I want exactly 1 mole, and let's just say that will be 5.00 because we're very precise in our lab. So we'll give ourselves 3 significant figures and call that 4.89. So you can see that made a big difference. Increasing the pressure like that made a big difference. We don't have nearly as much volume. Now we did increase the temperature too, which you would think would make the gas spread out a bit. And it would, but the difference between 273 and 298 isn't huge. It's not like we doubled the amount of heat in there, but we did increase the pressure a lot. So now we have 1 mole of gas in a much smaller container. So we could solve problems with this too. We can do it the same way that we did it before. And if we knew the volume of a gas, we could then do our division. And if we knew the moles of the gas, we could do a multiplication and do it exactly the same way we did the other problem. So this will be what we'll use in our lab.